Okay, so hi everyone. So one thing I wanted to cover in lecture, which I didn't get to do, is talk about some interesting applications of eigenvectors and eigenvalues, like in the world. So I'm going to start by talking about an application to technology, by which I mean an application to computer science. And this is a pretty famous application. This is related to search engines. So what's a search engine? Well, it's a website or it's a piece of software that, given a query, returns a list of relevant search results on the internet. Let's just say they're web pages. But you don't want to just list everything on the internet that has something to do with your query. You want to sort them according to importance. So you want to list the most important ones at the top, whatever that means. So the internet, really became popular in, I suppose, the 90s. And initially, there were a number of search engines up till 1997, which, for example, some examples were, Alta Vista, Lycos, previous versions of Yahoo. Not sure how many people are familiar with these, which were based on the following idea that, well, the importance of a web page should somehow be intrinsically defined. It should be related to the importance of the words in the web. And search engines were really not very good in the mid 90s, I would say. And they were based on this idea that you should rank according to some intrinsic measure of importance. And then in 1997, 98, there was a new search engine called Backrub, which came out. And this was based on this new idea, a new way of defining importance, which was that the importance of a web page should be proportional to the importance of the pages that link to it. And this is a very different idea. It's saying that importance is not intrinsically defined. It's a function of the, just the structure of the links on the internet, and it's somehow recursively defined. So what do I mean by this? Let me just show you by an example what this would mean. So here's a mini internet. So in 1997, it was much smaller than it is now. So let's say it was really small. Let's say it only had 4 web pages. And now let's draw some arrows for when web pages link to each other. So let's say the first web page has 3 links. It links to the second web page, third web page, and the fourth web page. And let's assign each of these arrows a weight, depending on how many links are on the source page. So each arrow gets a weight, which is 1 over the number of links on the source page. So since this web page has 3 links, we assign each of these a weight of 1. So this makes sense because if a web page has like 1,000 links, then you shouldn't treat each of them just as significantly as a web page that has 1 link. So I'm going to make this diagram with arrows and weights, where the weights are decided according to this formula. Okay, so let's say the second web page has 1 link. Then the third web page has 2 links. Okay, so arrow means 1 page links to another. May not be symmetric, of course. And then, well, let's say the fourth web page links to fourth. So now if you were to assign these things weights, this would get a weight of 1 because 2 only has one link. 4 would get halves over here. 3 would also get halves over here. Okay, so this is some sort of model of the internet that assigns every link a weight. And now, what was our formula? I mean, what was the idea behind backrub? Well, the idea was that the importance is proportional to the net importance of incoming links. So let's take the importance. And if we believe, that this is how importance works, then you should actually get some equations relating the importance of each web page to its neighbors. So, for example, the importance of x1 should be proportional to the sum of the incoming vectors, and the incoming importance, that's just x2, but it's not literally equal, it's proportional. So it's some coefficient of proportionality. And similarly, x2, so let's look at x2. It has 3 incoming links, one from each of the other 3 nodes. So this should be a third times x1 plus a half times x2 plus a half times x4, and again, only proportional, not literally equal. And now, okay, lambda times x3 is equal to a third times x1 plus a half times x4, and lambda times x4 is equal to a third times x1 plus a half times x3. So the question is, what are some importance scores that satisfy these equations? And the punchline is that, well, this is just an eigenvector equation. This is just the equation lambda x equals ax for a matrix A, a 4x4 matrix, with entries, corresponding to these weights. So 0, 1, 0, 0, a third, half, I'm sorry, oops. So x2 doesn't get a weight from itself, right? This is 3, a half, and then you have a third, 0, 0, half, and a third, 0, half, 0. So the point is, this is an eigenvector equation. And so you can solve this, and you get that actually the following vector is an eigenvector. It's a vector 12, 4, 9, 6. This is an eigenvector with eigenvalue lambda equals 1. You can solve this using the techniques we learned in this course. And the point is, this gives you some ranking of the web pages in terms of how important they are. For example, x1 has the highest score, so this is number 1. Second highest score is x3, so this is number 2. Third highest score is x4, so this is number 3. And this is x4. So by solving an eigenvector equation that you get from the internet like this, you actually get a ranking of the vertices. And you can prove that if you set the weights up this way, you always get an eigenvalue of 1. We won't prove that in this course. You can try to prove it. It's actually not hard. And the punchline is that this scheme of ranking web pages did way better than everything else. And actually, this thing backrub, this is what became Google eventually, which we all use now. And this scheme of using eigenvector to rank web pages is called PageRank, named after Larry Page, who was one of the co-founders of Google. So Eigenvectors and eigenvalues are used throughout modern computer science. I mean, the heart of like Netflix and Amazon and most of the other recommender systems are somehow based on eigenvectors and eigenvalues, specifically the singular value decomposition, which we'll study later. So that's one application of eigenvectors and eigenvalues to technology. Let me tell you a little bit about the, I guess, interpretation in science and engineering. The interpretation here is that, well, usually you model some physical process, either in classical mechanics or quantum mechanics. I mean, I don't want to get into the details of this, but ultimately you somehow model this by a matrix. And then you have these physical phenomena of resonant frequencies and resonant modes of various objects, like, a resonant frequency of a physical object is a frequency such that if you vibrate it at that frequency, it'll continue to vibrate at the same frequency. It won't change. For example, a musical instrument. So these correspond to eigenvalues and resonant. Resonant modes, which a resonant mode is the actual wave, the actual shape of the vibration at the resonant frequency. This corresponds to an eigenvector. So I mean, if you study science or engineering, you'll see lots of this later in your life. But eigenvalues have a physical meaning. They're these resonant frequencies of various physical systems. And finally, I want to talk about a phenomenon of universality, which connects a lot of different phenomena in science, engineering, society, technology, like many different aspects of the world, which are related to eigenvalues. So this is an active research area. It's not that well understood. So what I want to say is that, well, you can consider the following 3 experiments. So the first experiment, experiment 1, experiment in physics, or maybe chemistry. The experiment is, well, take a heavy nucleus, for example, uranium, so the high atomic number. And as you know, in chemistry, the electrons appear at these energy levels, right? So there's a nucleus, and then there are these electrons that appear at different distances. And what you could do is you could plot the first 1,000 energy levels. And actually what you could do is you could pick 2 random levels, don't have to be adjacent, and plot the spacings between them. So if you pick 2 at random, you get some statistical distribution as a mean standard deviation of what the spacing is. Plot that. Here's a second experiment you could do, which is a math experiment. And here, what you can do is you can choose 1,000, large consecutive primes. And again, plot the spacing distribution. Pick 2 at random and just look at the histogram of spacing. Or just, plot the distribution. The third example, which comes from statistics and is most related to this course, is generate a 1,000 by 1,000 random symmetric matrix. So symmetric matrix is one that's equal to its transpose. So that means Aij is equal to Aji. And what that, in the following way, just set Aij equal to Aji to be +1 with probability a half and -1 with probability a half. So for every entry, just flip a coin and put a +1 or -1. And now plot the eigenvalues, which are going to be 1,000 numbers, which are actually going to be real, as we'll prove in a couple of lectures. We have a symmetric matrix eigenvalues are real. We haven't proved that yet, but we will. So these are 3 different experiments from very different walks of life. Right? One is from physics, one is from math, the other is from probability or statistics. And what should the energy levels of a nucleus have to do with prime numbers, and what should that have to do with eigenvalues of a random matrix, right? So the punchline here is, if you do this, then you get the following plot. So these are various distributions, and the 3 that I talked about. So experiment 1, which was the heavy nucleus, was this one. It's called erbium, which is apparently some heavy element. Experiment 2, which really you plot the zeros of the Riemann zeta function, which is related to primes, is this. Okay. So, okay, I said primes, but really you need to do some change of variables, but this is related to primes. And then experiment 3 is eigenvalues of a random matrix. And the punchline is that these look very much the same. So it's observed empirically that many different phenomena in nature, including these 3, have the same statistics, and they all look like eigenvalues of a random matrix. And so this is really one of the biggest mysteries in science right now. Nobody knows why this is happening, right? Somehow what this is pointing to is that all these 3 things have the same statistics. And so there's this somehow there's this question that, is there some underlying some universal matrix that underlies all these phenomena, and nobody knows. So this is really this is called universality. It's this observation that eigenvalues of randomly generated matrices describe many phenomena in reality, including in physics, like this nucleus, including in number theory, and even more generally, like there's all kinds of other things here. Like there's a well, I don't know if this one is here, but there are certain statistics from traffic actually that follow the same distribution. So, I mean, the point I want to make is that eigenvalues are really out there in many different aspects of reality. So anyway, that's it.